Welcome to Lecture 10 in GRA 6036. Today is March 26. I've gotten requests about more math exercises and with proposed solutions so that you have more stuff to work with to prepare for the exams. And so I now made an exercise set that will be uploaded on It's Learning later today. I strongly advise you to try the exercises in the exercise set, and if you prove for me that you tried to solve the exercises, I'll give out the proposed solutions. So that exercise set will be made available today. And I've also now made a Q&A forum on It's Learning, so you can feel free to ask any course-related question on that forum. So these are the two messages of today. These two. Okay, so today you will work with project 13, and we'll sit ready under a designated video on YouTube and answer your questions related to project 13. So in that project, you'll continue working with the beauty dataset. And to this dataset, you'll fit various regression models, and you are asked to assess their fit, so how well they track the trend or in the data. And to do so, you'll be looking at the residuals. So let's now look at what residuals are and what they are supposed to look like, because in order to say that, well, the residuals look bad, you have to know what good-looking residuals look like. Okay, so remember that we split this data set in two, and so you'll do that in the project. So you'll make one data set for the good-looking people and one data set for the not so good-looking people. So let's make a variable called GL that takes the value 1 if looks is assessed to be about 3. And then we can make a new data set. So we subset the big data set, so the BTY data set. So now I'm making a data set that only contains the good-looking people. So you can have a look at this data set, BTY GL. Okay, so here you see there is only GL is equal to 1 for all the individuals in this data set. So suppose we want to fit a linear regression model on this data set with log wage as our dependent variable and years of workforce experience as our independent variable. So in the notation we use when we write this in our notebook, then y, so we want to fit a model a plus b times x plus noise, where a and b are, or maybe we should write beta 0, beta 1 are the unknown parameters that we are to estimate from the data. So when we say that log wage is our dependent variable, that means that in this equation y is equal to what is here, b2i GL log wage, while x is equal to BTY GL expr. Okay, because these are the variable names that are in this. So here, and expr is here. Okay. So we would like to fit this model to the data and then later on assess its fit. So first thing to do, a good habit, is to plot. I mean, when we have a regression model like this with only one x, so we can plot the data. It's nice to plot the data. So let's plot the data. So then this is our x and log wage is our y. And I remove the frames. So then you get this plot. Okay, so this is where we're supposed to see, well, I mean, so we look at this data and we think, well, maybe a linear regression model, or maybe this regression model here will give a decent fit. So we fit this model, so that's our fit 1, LM. Then, as you know, the syntax in LM is that you have the dependent variable tilde the independent variable. So now we fitted this model, so you can run summary on this fit object to have a look at, well, the estimated coefficient. So this is the estimate of beta 0, while this is the estimate of beta 1, and these are the p-values that you'll work with in project 13. And so after having done summary, you also know that to access these estimated coefficients, instead of copying them and pasting them into your script, you can do fit $1 coef. Then you get the coefficients, and to get the intercept you do 1, and to get the slope you do 2, and if there are more estimated coefficients, you can do 3, 4, and so on. Okay, so let's make the residuals. So the residuals are the differences between the observations y and the predicted values y hat. So what we often denote as well, write y with an hat above, and when we write in our notebook, so that is then equal to the estimated parameter beta 0 hat plus beta 1 hat. So these are the estimates times x. Okay, so let's call our residual RR. So then our y is this one. So we are to take minus y hat, but to do so we need to make a y hat. So our y hat here is then the estimated intercept plus the estimated slope times the independent of the covariate. So this is then our y hat, and we can now make our residuals, and we can plot the residuals. So you plot the residuals by having the covariate on the x-axis and then the residuals. Now I again move the frames to that plot because I don't like these frames. So just to show you what the frame plot is doing, if you plot it with frames, you get this box. So if you do what I like to do, take the frame plot false, you remove this box. It looks nicer. Okay, so this is a plot of the residuals. Well, to know whether or not this is good or bad, we should know something about what it is supposed to look like when it is good. So then we can see if it's if this plot deviates from something good. So to do so, we can, and this is a trick that you should. If you have questions like this, well, is it good or bad, or what is it supposed to look like? I mean, then go to do simulations. Okay, so let's simulate some regression data. So simulating some regression data means that we make data where we know the truth, So where everything is perfect, so we fit the perfect model to our simulated data, and then we make the residuals. Okay, so let's say we have a, first to simulate a regression, we need a covariate. So let's say that our covariate is just, we need a number of individuals. So let's say we have 200 units or individuals or whatever, and then we simulate some covariates, or just make some covariates. So we need one for each individual over the unit interval. This runif means random uniforms. So this function draws numbers between 0 and 1 with the same probability for each number. Okay, so we run, so we have to make n, then we run this. So now we have our covariate. And now comes the part where we play, God, or some, where we know the truth, because now we set the parameters of our regression model. So let's say that the intercept, okay, let's call it beta 0, the intercept is 0.54. So now we know the truth in this model. We know that the intercept is 0.54, and we also know that the slope is 1.58. So now we're getting closer to making a simulating data. But so these are the x's. We also need the y's. So the y's will be beta 0 plus beta 1 times the covariate plus mean 0 noise. Well, we need to make noise, and now so to make the noise we need one noise term for each individual. And let's so this is a typical assumption is that the noise terms are normal or close to being normal. So we need as many as there are individuals. They have mean 0, and then they have some variance. So let's say they have 1/5. That's the variance. So if we now run this code, well, we need to run everything. Now we have our x's, they are here, and our y's. We could even make that into a data set using the, I think it's the cbind command. So if you do this, we get something that looks like a data set. So, which is a data set. It's a simulated data set. So here we have y, x. Okay. So now we can, well, we can make a plot of x and y to see what our simulated data looks like. Well, so I mean here you see that this is the perfect setting. So to say for fitting a simple linear regression model, which is not strange because we simulated our data from this model. So we made it look like this. But the point is that well, now we can plot the residuals and see how things are supposed to look when we actually know the underlying truth. Okay, so so there's something to notice here is that in this data that I simulated, and this is an assumption of when we do linear regression, is that the noise term has a mean 0 and has a variance or a standard deviation here that is the same no matter what the value of x is. So there's a constant variance noise that does not depend on x. So notice that if we take this plot and overlay the a line. So we make so then we can do abline beta. Here is the true line, so beta 0, beta 1. Color, let's make it green. The line with 1.5 thick. We do this. So this is the true line. So that's this function right here that we plotted. And notice that if you look at the variance of these dots around this line, it seems to be about the same. It is the same variance about this line, no matter where on the x-axis you are. Okay, so that is called the assumption of homoscedasticity or something. Look it up. It's hard to pronounce. Well, so now we go to our residuals. So now we pretend that that we have these data x and y, but we don't know. We pretend that we do not know these values. So we fit a model. So this is fit sims. So we're fitting the data on the simulations. Then we do y, x. We fit the model. We can look at the summary of this fit sims. It's here. So we see that we made the game rather easy for ourselves because for many reasons. But we see that our estimates are extremely close to the true values. So see, this number is extremely close to this number, and this number is extremely close to this number. So not surprisingly, we get good estimates in this case. And we can then make our residuals. So let's call them RR sims. So they are then y, observed y's minus the fitted lines. So then we do fit sims coef1 minus fit sims $ coef2 times x. So now we made our residuals, and we can plot these residuals are our sims. Well, we have to have x on the x-axis are our sims. So we plot these, and this is our plot. So in this plot, there are this is then a plot of the residuals where the model will fit into the data. Let's see. Where's the LM function? This one is the perfect model. So if you fit the perfect model, this is one example of what your residuals might look like. So here are a few things to notice. First, notice that if we draw a straight line, at 0, we see that, the residuals are centered around 0, so the residuals have mean 0, which they theoretically should have. You have an exercise to that effect in the extra exercises project that I'll put out. But so that, they're supposed to have mean 0, which you can see from this plot that, indeed they do have mean 0. And you can also sort of see from the plot that the variance of the residuals around 0 is the same no matter where you are on the x-axis. Okay, so this is what it's supposed to look like. Now, to make it, we can do this. Let's now do the same. Maybe it's easier to see if we do the same simulations with more individuals. So we go up from 200. So we had 200. Let's write it down. Remember it, to 500, and we do everything once again. now it might be even easier to see that our model is extremely good. Okay, so in the next video, I'll continue my talk about residuals and look at residuals in the beauty dataset.